Hi guys, and welcome to Introduction to Mechanical and Automotive Engineering. I'm your lecturer, Dr. Elizabeth Kiriakou, and last week we've been working on problems that are going to be similar to the mid-semester exam. So here we have question 5.40, and those who have the textbook, this comes out of the textbook of Hibbler. And in this question, it asks us to determine the horizontal and vertical components at pins A and B exerted onto the frame. So we know that we need to find AY and AX and BY and BX. So we have two pins here, which means we're going to have a indeterminate solution. So we need to take a look at the frame and see how can we break this problem up into multiple components. So if I take a look here, because it's a frame at B, E, C and F, they're all pin joints. So at all these joints we're going to have an X and a Y component. Okay? So how can I break this problem up and actually simplify it? So if I take a section through here, let's see what we have. So first of all, we're going to look at member AD, and then we're going to look at member BC. So over here, we just have member AD, and I'm just going to clean this up. And over here, we're going to have member BC. So on this side, we're going to have A and B, D, sorry, and we also have a point at E. So we can take the member at BD and actually draw that as a force. Okay, and this one's going away from the joint. And if we take a look at E, we have this member EF, and it's on an angle. So we can call that EF. We know that at A, we're going to have a reaction force. So we're going to have AY and AX. And we also have a distributed load that we need to turn into a concentrated force, and we need to calculate that. If I take a look now at member BC, things have to be equal and opposite for it to stay in equilibrium. So here is member B, and that's C, and here we have F. So on this side, I drew it going away from the point, so this way. At C, it also has to be the same. So these two forces actually need to cancel out. And then again, we have the member, and it has to be equal and opposite. Let's just write that equal and opposite. So it's going to actually go in this direction. So it's going to be EF. Again, these two forces, for our system to be in equilibrium, they need to cancel each other out. So if I just write out my equations for equilibrium, I'm going to have some of the forces in the x direction has to equal 0, some of the forces in the y direction has to equal 0, and some of the moments around a point has to equal 0. And again, we need to find out what our reaction forces are at B. So we're going to have a BY and a BX. So I've now set this up as two separate problems. Let's calculate what this distributed load needs to be. So if I just draw this down here, and here I have 400 newtons on the metre, and my distance is going to be 3 plus 1.5, so that's 4.5 metres. And my distributed load is the length times the breadth, so it's going to be 4.5 metres times 400 newtons on the metre. So my metres will cancel out and I'm going to be left with 4.5 times 400. So, and that's where that's going to sit. That's going to sit halfway along this beam, and that's at 2.25 metres, and this is 4.5 times 400 newtons. Okay, so I have quite a few unknowns here, but if I take some of the moments around A, I'm actually going to be able to write an expression for EF and CD. And if I do the same thing on this side of the member, if I take some of the moments around B, I'm again going to have an expression for EF and CD. So I think I'm going to end up with a couple of simultaneous equations here. So let's just start by solving. If we take some of the moments in this problem, so some of the moments around A has to equal 0. What do we need to do with this force? We need to break it up into its horizontal and vertical components. And here I actually have a triangle of 3, 4, 5, and we can get that from the diagram. And I'm going to have an x component, so I'll have here EF 4 and 5, and I'll have a vertical component, and that's going to be EF 3 on 5. So now I can take some of the moments around A. So the first force we have is, let's actually put small dimensions in here. So from here to here is 4.5 metres, and is that the only, and we need to know what the height is of E, and this height here from E to A is actually 3 metres. So some of the moments around A is going to equal 0. We have the DC, and that's going in the negative direction. So we're going to have minus DC, my perpendicular distance is 4.5. And what else do we have? We have the x component of EF, and that's going to go in the positive direction, so plus EF 4 on 5. And my perpendicular distance is 3 metres. And I also have my distributed load, so that's 4.5 times 400. My perpendicular distance is 2.25 metres, and that is going in the negative direction. So I'm going to have this as equation number 1. Now, if I take some of the moments, if I look at this member, some of the moments around B, I'm going to have pretty much the same thing. Here I have my triangle, I have 5, 3 and 4. So I'm going to have an x and a y component. So here I'll have EF 3 on 5, and in the x direction I'm going to have EF 4 on 5. So I need to have some distances again from F to B is 1.5 metres, and from F to C is 3.5 metres, or 3 metres, sorry. So if I take some of the moments around B, I'm going to be able to find an expression in terms of DC and EF also. So let's take a look. So some of the moments around B has to equal 0. And which component we're going to have? We're going to have the EF in the horizontal. So we have EF 4 on 5. And our perpendicular distance is 1.5 metres. And that's going in the negative direction. And we also have DC, and that's going positive, so it'll be plus DC, and my perpendicular distance is 4.5 metres. So this is going to be equation number 2. So if I solve these two equations simultaneously, I'm actually going to have a value for EF and DC. So I can solve, I'll let you solve that. Solve equation 1 and 2, and EF is going to equal 3375 newtons, and DC is going to equal 900 newtons. Okay, so once we have these two values, now we can go back to our respective free body diagrams and look at these two equations of equilibrium, some of the forces in the x direction, which equals 0, and some of the forces in the y direction. So if we take a look at this problem, I'm just going to clean this part up. So over here I'm just going to write what my numbers are. So EF equals 3375 newtons and DC equals 900 newtons. So let's take a look at this member. So if I say sum of the forces in the x direction equals 0, I should be able to find AX over here. So what do we have? We have DC, and that's positive. So let's just draw an axis here, y and x. And I also have the x component, so minus EF 4 on 5 plus AX. So I can just substitute these numbers in, and I'm going to have 0 equals 900 minus 3375 4 on 5 plus AX. So when you solve that, AX is going to equal 0. Now to find the y component, AY, we can say that sum of the forces in the y direction equals 0. So let's write that over here. So sum of the forces in the y direction has to equal 0, and what do we have in the y direction? We have minus AY and plus EF, let's say 3 on 5. So I'm going to substitute that value in, and AY is going to equal 2025 newtons. Okay, so now I've found my components at A. Now I'm going to do exactly the same thing and find the components at B. So AX equals 0, AY equals 2025 newtons. And if I take a look at member BC, I have the value for EF and DC, and they're always equal and opposite to make sure that my system is in equilibrium. And let's solve it. So sum of the forces in the x direction is going to give me bx, and sum of the forces in the y direction is going to give me by. So let's say sum of the forces in the x direction has to equal 0. What do we have in the x direction? We have this member and this member. So we're going to have minus dc minus bx plus EF 4 on 5. So if I substitute in some numbers, I'm going to have bx on this side, I'll have minus 900 plus 3375 4 on 5. And then what do we have? bx is going to be 1800 newtons. So now we can say sum of the forces in the y direction is going to give me by. So sum of the forces in the y direction equals 0. And what do we have in the y? We just have the y component of EF. So that's going negative EF 315 minus or plus BY. So BY is going to equal 2025 newtons. So there we found our x and our y components for the pin joints at A and B. There we have it.